Alright, good evening everyone. So, I think a few more people will join now, I guess. So, let's start our discussion today. Let the others join. Uh, so, before I start, if you have any quick questions, you can ask. Does anyone have any questions? Let me check the name.
Hello.
Yes, Kiranjit. Kiranjot.
Hello.
Hello.
I had a question regarding lecture 12.
Okay.
Sorry, I was not able to ask it in the previous meeting.
Okay, no
So,
problem.
in the lecture 12, it was said that many times it is stated that during overexpansion,
Mm-hmm.
we experience a side thrust during the oblique shocks being formed.
Mm-hmm. Yeah.
Yes, but oblique shocks are also formed when under expansion happens. So why are not we experiencing side thrust in that? And why is it being morely concentrated when we are talking about over expansion?
See, oblique shocks occurs when there is a over expansion only. If it is under expansion, first initially you will have a expansion wave first, and then you will have oblique shocks. Oblique shocks will be outside the nozzle, which we are not interested in. If the oblique shock is inside the nozzle or near the outlet, then only we have all sorts of these performance issues. So, do you
So how is this side thrust like being created?
like it's okay? Side thrust is because you will have a flow separation happening, right? So
Yes, sir.
how do I draw this? Let's say, so let's say if you have something like this, you have a nozzle like this, okay, or let's say a conical nozzle, and now let's say you have under expansion. So let's first start with over expansion, okay. So let's say you have over expansion. So over expansion, what it means is your P exit will be less than or greater than P ambient. How will it be over expansion? Will it be less than or will it be greater than? So if it's an
So less than.
so basically if it's over expansion means your exit pressure would be less than the ambient pressure. Reason is you have over expanded it. Expansion means drop in pressure. So ideal expansion is when you have P exit equal to P ambient. Okay, and if you are over expanding means you have passed that pressure. So you have passed the ambient pressure and you expanded more. So expansion means reduction in pressure. So please remember that. So what happens? Your pressure has gone down. Okay, and outside the pressure is ambient. So what you need is you need to reach the ambient pressure. So if you want to reach the ambient pressure, you have low pressure here, you have high pressure here. So immediately what it happens is only the pressure jump can happen only if you have any shock. Okay, either it can be normal shock or it can be oblique shock, that doesn't matter, but the pressure jump can happen only if there is a shock. So uh, whether normal shock happens or oblique shock happens depends upon this pressure difference PE and PA. So since PE and PA will not be strong enough to have a normal shock, what usually happens is first it forms a oblique shock. Okay, so somewhere over here it formed something like an oblique shock. Let's say this is the center line. So it forms like something like an oblique shock. Okay, so first it forms like an oblique shock, and the flow which was coming like this, since So what shock does is it always turns the flow to itself. Okay, so which means your flow area is converging. So you what actually happens is your flow will uh, turn towards the center line. Okay, but what also happens is usually there will be a since so what happens here it will be, since PE will be less than PA here, so the shock what it makes is it makes PE to be equal to PA, so whatever the pressure here will be equal to PA. Okay, so the and what you have here is here you have low pressure, here you have low pressure, here you have ambient pressure, so there can be flow reversals happen here. And yeah, ideally what it forms is it forms a shear layer, something like this. Okay, and the growth of shear layer is dependent on whether there is a shock next or not. Okay, so what happens is after this oblique shock, since the flows towards the center line, it has to maintain the mass conservation. So there is something called center line boundary conditions, so flow cannot converge to a center line, so it has to turn and become straight, right? So what happens is this another reflected shock will form, which makes the flow to be straight. Okay, and after that what happens, after that what happens after that, you need to you will have something like a uh, how will it be, expansion wave. You will have something like an expansion wave, right? And then you will have reflected expansion waves. So these things will keep on going on. Okay, but what happens is here the the nozzle near the exit, since you have a shock, the flow becomes subsonic here. Okay, and because of this there is a high chances of flow separation happening over here. This shear layer will tell the flow separation, which means here there is a flow separations basically. Okay, this flow separation leads through the side thrust, which we usually talk about. Okay, but the same thing doesn't happen in the under expansion. Let me draw under expansion also. So how does under expansion works? So under expansion means PE is greater than PA. So let me draw that also. Let's say if you have a nozzle something like this. Okay, now since PE is, so the flow is coming out like this, PE is greater than PA. Okay, which means you still have a lot of potential to expand it to atmosphere. Okay, which means you haven't expanded to an ideal state. That's what under expansion means. So that's why PE is greater than PA, and hence what happens now, PE is higher and PA is lower, so you need to reduce the pressure. So how do you reduce the pressure? Is through expansion waves. So remember, if you want to increase the pressure, there should be a shock wave, and if you want to reduce the pressure, there should be an expansion wave. And all these things happens only in the supersonic flow. Okay, it doesn't happen in the subsonic flow. There is no such thing called shock in a subsonic flow. Okay, so since the flow is supersonic and you want to increase the pressure, what you have to do is you have to expand it even more. So expansion is caused by the expansion waves. So what this expansion wave does is, so this is how the flow comes. Now you want to expand it, which means the flow to reach the ambient pressure. So what happens is there will be a expansion waves, something like this. Okay, and this will not be inside the nozzle. Okay, understand that this will not be inside the nozzle. It will be near the exit of the nozzle. So ideally what happens, the exit is where you are finding the thrust. Okay, This is where VE you find, this is where m dot exit you will find, and this is what it is going to give us thrust. And since the expansion is just at the exit, and also expansion wave, what it does is it tries to move the flow outside like this. Okay, so it tries to move the flow outside like this will make PE equal to PA. And if you look at the shear layer at this point, okay, it will be something like this. And then it converges based on the reflected expansion waves, all sorts of things. Okay, so the shear layer would be little outward, okay, which is not going to create any side thrust. So in fact, the side thrust, when we talk about side thrust, it's I'm talking here about side thrust will always be there because the flow is not straight. It is a little, so streamlines, if you draw the streamlines here, how it will look, so it will look something like this. So there is, with an angle, it always goes out. Okay, that is that will also cause the side thrust. But what happens is, in this case, the side thrust caused is balanced each other. So since it's a circular, whatever the side thrust caused is radially outward, and it is balanced each other. But if there is a flow separation happening, something like this will be highly turbulent, and the turbulent flows, in that case, there won't be balancing of side thrust happening, and hence there will be any unbalanced forces. Okay, so uh, that is the problem being over expansion. If it's an under expansion, it can nicely balance out. Okay, and also the shear layer is going to expand like this since it's under expansion, and that is not going to create any unbalanced side thrust in our system. So in that way, it's good for us. Is that clear?
Yes, sir.
Okay, so basically this flow separation is kind of like fatal for operation, but you cannot avoid it, it's just the nature. Anyway, um, we have a few students here. Okay, so if you have any doubts, what we can do is we can quickly finish. I have two questions today. We can quickly finish this, and then if you have doubts, we can discuss later, maybe like 8 o'clock or something like that. Okay, so this is these two questions are fairly straightforward for you guys, and provided we already solved a few sections of this question, so I might even skip some of the questions here. So what do I have here is, so this is regarding the performance of the nozzle. The first question is regarding the performance of the nozzle. So here, the question, let's read the question. Synthin is a synthetic fuel developed by USSR in early 1960s and was widely used in their rockets between 1970 and 1980. So this is some general information. It's not really required for solving the question, but it's interesting. That's why I kept it. So this is kind of like a synthetic fuel developed by Russia back then in 1960s. So so what this propellant, what this fuel contain is, it contains synthetic kerosene as a fuel and liquid oxygen as a oxidizer. Okay, this is the fuel and this will be the oxidizer. And the properties of the exhaust gas are, as the specific heat ratio of 1.24, molecular weight is also given, and the propellant mass flow rate is given. Okay, this is the some properties of exhaust gas, and the combustion chamber pressure and temperature are this and this, okay, respectively. The nozzle is designed for an optimum expansion at sea level condition. So they are designing it for a sea level condition. Now what we were asked to find is, we are asked to calculate the throat area, temperature and pressure, okay, and exit Mach number, expansion ratio, and then you have ideal thrust coefficient we need to find. We already did it in the last class itself. and it's also straightforward implementation of you need to just use the equations in order to get this. And similarly the thrust coefficient and also specific impulse, these things we already did last time, so maybe I will leave it up to you to calculate it. First three we will calculate, okay. And this one is, if semi divergence angle is 15 degrees, calculate the divergence loss coefficient, okay. So this is because the nozzle is uh, has a divergence angle of 15 degrees. Not all the flow is going to give us the thrust, okay. Some of the thrust is lost because it's the flow is not straight, as I explained before. Flow is not in the along the axial direction. It some component is in the radial direction also. So because of that we lost some of the thrust. That is what we were asked to find out: fractional loss in thrust. Determine the exit area of the nozzle, that we can find once we know the expansion ratio. And also divergent length of the nozzle. What is the length of your nozzle is what we need to find, okay. So let's quickly solve this. So let's see. First is we need to find uh, throat area, temperature and pressure, okay. So what are the things given? So it's like chamber temperature is given 3670 Kelvin, and chamber pressure is given 35 atmosphere, and also molecular weight of the gases are given. So 23.30 kilogram per kilomole, and specific heat ratio is 1.24. See, all these are like the parameters coming from the combustion chamber. So what you will study is these things you already know, but how do we get these parameters? It's what you will be studying in, I know, week 5 or week 6 lectures will be dealing with this, okay. So basically this is a product of the combustion of a propellant, okay. In our case it's just kerosene and liquid oxygen. When it combusts, this is the temperature it reaches in the chamber and also the pressure it reaches in the chamber. And because of this combustion, carbon dioxide, hydrogen, water vapor, all these things are going to form. And whatever the gas you have, it is going to be a mixture of all these gases, and the molecular weight of that gas mixture, okay, gas mixture is what is given: molecular weight and specific heat ratio. So this is like an inlet to the nozzle, okay. And what is also given is mass flow rate. Mass flow rate is 400 kg per second. This is the mass flow rate flowing through the nozzle. Alright, so now what we were asked to find is, we need to find area of the throat, temperature at the throat and the pressure at the throat. This is what we need to find. Alright, so how do we start this problem? How can we solve this? So in the meanwhile, let me draw the diagram. This is the diameter of the throat, and this will be exit diameter. So we were asked to find what is the temperature at the throat. This is the throat, so we need to find TT and PT, and also DT. What is this? This is also we need to find. So how do we find it? Anyone have any guess?
So formula we'll have to use those
Yeah.
pressure ratio and temperature ratios.
So what is that formula about? We have to use formula. There are a bunch of formulas, but we should know what are those formulas, right?
So I also wanted to ask about that. There are so many formulas and they are very lengthy and complex. So
Hmm.
will some of them be given in the question during the exam?
Hmm.
Because
Probably if
it's
the question you involves like, I'm not very sure if the, let's say for example the expansion ratio formula is very big, right? And
yes, yes, sir.
but
Even area ratio
velocity of the
formula.
area ratio formula is very big, but the velocity of the exit vj jet velocity formula, those things you should,
That
those
is
things you should remember, because it is something you can easily remember. But these are little difficult, I understand. Probably they might give uh, during the exam, but I will once confirm that with professor and I will let you know about it. Okay.
all right, sir.
uh, I'm not sure what happened last semesters and all, but yeah, I will confirm with professor about it. So yeah, coming back to the question, how do we find the total temperature and pressure?
Sir, the formula for throat temperature to throat to combustion chamber temperature is 2 upon 1 gamma plus 1
Okay, tt by tc
TC.
divided equal to 2 by gamma plus 1. But what is this temperature? What is this relation? Is the question. So this relation is right actually. You whatever you gave is right, but we need to understand why we are writing this temperature equation something like this. Okay. So,
Yeah, it has a derivation.
but what is the principle behind it? Okay, no problem. I will tell you. So basically, there is
Initially,
this.
they had sir had given that control volume treatment of the nozzle vent kind of all
Hmm.
the time I remember.
Okay, so basically, this is coming from.
To apply steady flow energy equation.
Right, steady flow energy equation. Yeah. So this is actually coming from steady flow energy equation. In fact, you might remember. So one of few assumptions that we take during the nozzle derivation is this is isentropic process. Okay. So this is one of the assumptions we make. This is the isentropic process happening in the nozzle. Okay, and because of this, what you can write is, if it's an isentropic process, you can use isentropic relations. Okay, there is compressible flow relations, isentropic flow relations. What it actually tells is, it just says the total temperature or stagnation temperature divided by the temperature, or I think it's the other way around. So T by T stagnation is equal to 1 plus gamma minus 1 by 2 into m square. Okay, this is actually a compressible flow relation. It's for an isentropic process, isentropic flows basically. This is an isentropic flow. It's not process, it's flow. Okay, I recommend you guys to go and look into this isentropic flow, because that is one of the main assumption we did for this nozzle. Okay, that is how we get all these relations. We are just telling that there is no any irreversibilities happening in the nozzle, uh, and based on that, and also it's adiabatic, there is no heat loss across the nozzle, but in reality that is not the case. All these things are there. Okay, so uh, so from the flow relations, what you have is, you have this, since it's an isentropic flow, you can write like, if let it be any flow. Okay, you have something called stagnation temperature. How do you get this stagnation temperature? Let's say if you have a flow, and if you isentropically decelerate it to zero velocity. Okay, let's say you have a flow with some velocity, you decelerate that flow to a zero velocity. When you decelerate it, since it's an isentropic flow, its temperature increases, and the temperature when it's 0 is what we call it as a stagnation temperature, and that is what this TT is. Okay, so basically based on the flow velocity you can find what would be the actual temperature of the flow. Okay, so the flow velocity can be given as a Mach number. Once you give Mach number, and if you know the stagnation temperature, you can actually find the temperature at any point in the flow based on the Mach number. Okay, that is the relation. You guys should go and look into it. It's a compressible flow relation. Okay, and also its derivation. It's pretty straightforward. This is how it is defined, in fact. Okay, so this we are going to apply it for the throat. Okay, and we all know if it is a choked nozzle, if the nozzle is choked at the throat, Mach number is going to be 1. So if you make this one Mach number to be 1, then what happens, this relation boils down to this. Okay, this relation. So since you will have 1, you will be like gamma plus 1 by 2. This is what is written in reciprocal form. It is written by 2 by gamma plus 1. Okay, so basically this is coming from an isentropic flow relation. Okay, so but in order to use this you should have a choked flow. So basically that is not been given here, but we are going to, usually it should be given, but for some reason this question doesn't have. So basically we are going to assume this is a choked mass flow rate. Okay, so basically we are assuming nozzle is choked. So if the nozzle is choked, we know the Mach number to be at the throat to be equal to 1. So this is how you get this relation. Okay, and based on that, now it is straightforward for you to find TC. So it's TC into 2 by gamma plus 1. Okay, and TC and all other things are given, so it's straightforward. TC into 2 divided by 1.24 plus 1. So how much is TT coming out to be?
So 3276.79 Kelvin.
3276.79 Kelvin. Alright. Now we can also find PT. So this is also from the isentropic relations you can find PT. Or if you have, since you know temperature at one more thing I forgot to tell is this is the chamber. You have TC and PC, and the chamber is where we fix the stagnation, because at the chamber the velocity is nearly 0, so we take TC as a stagnation temperature for this, and that is how this TT become actually TC. Okay, I think there will be a lot of confusion here. Let me put it TS as a stagnation temperature, and T is at any temperature. So so T is at the throat and TS is actually stagnation temperature, and here we are taking stagnation temperature to be equal to the combustion chamber temperature, because we are approximating that velocity in the combustion chamber is nearly equal to 0, which is, and that temperature is going to be close to the stagnation temperature, so that's why we are taking that. Okay, so from flow here to here is basically isentropic, is what we are telling. In fact, the flow is isentropic throughout the nozzle. So yeah, so basically similarly you can use the stagnation pressure or the concept of stagnation pressure here. Also you can also use it, since it's an adiabatic process from chamber to the throat. It's an adiabatic process from the chamber to the throat. The flow is going to be adiabatic. We know for an adiabatic process how it is going to behave. Is thermodynamics 101. So based on that also you can find what you call the throat pressure. Okay, so let's write down the relation for PT. So how does that look? So I have it somewhere here. So PT by PC is equal to, you can write the same thing, let me write down the expression for this: gamma minus 1 by 2 into m square whole power gamma by gamma minus 1. Okay, or the other way, let me write it in terms of throat and chamber pressure. So P of throat by P of chamber is going to be equal to 2 by gamma plus 1 whole power gamma by gamma minus 1. So it's basically after substituting this Mach number to be 1, or you can also write this as, this is basically coming from adiabatic relation, whole power gamma minus 1 by gamma. Okay, so this is what, so I just replaced this with 2 by gamma plus 1 for easily, you can easily find it. So let's say if you substitute this PC into 2 by gamma plus 1 gamma by gamma minus 1, PC is, I guess it's 35 atmospheres, right? It's 35 into 101,325. You can just keep it as atmosphere also. You can express PT also in terms of atmospheres, and divided by 1.24 plus 1 whole power 1.24 by 0.24. So how much is PT?
I guess 19.49 atmosphere.
19.49 atmosphere. Right. So basically you can see that the pressure and temperature actually both are decreasing. Okay, and velocity is increasing. That's the conversion from thermal energy to kinetic energy. All right, that is done. So, and we need to find area of the throat. Now how do we find area of the throat? What is the area of the throat? Is there a formula for that? Very good. We don't have any formula, explicit formula for that. And now I need to find area of throat. How can I find it? So you can use this mass flow rate. Basically the mass flow rate, if area of throat, what it defines is, it's going to define how much mass I'm going to so if I increase the area of the throat, I am going to have higher mass flow rate. Okay, so basically you can try to find the mass area of the throat from the mass flow rate, and mass flow rate is going to be constant, that is mass conservation. So mass flow rate, you can write it as rho t, at, and vt, velocity at the throat, right? And what we know about velocity at the throat, it is going to be Mach number equal to 1, m is equal to 1, which means velocity at the throat is going to be same as the speed of the sound. So this you can replace it as gamma r into throat temperature of the throat. Okay, so in that way velocity of the throat is known, mass flow rate is known, How about density of the throat? Density of the throat is going to be, density of gases at the throat is going to be, you can use ideal gas relation, P by rho, sorry, P by R T. Okay, so this will, since we know P and T, you can find the density at the throat, and once you find the density at the throat, you can easily find the area at the throat, right? And yeah, so let's try to find it out. M dot is equal to m dot by rho t vt. So this is given as 400 kg per second, and rho t you can write it as pt by rtt, and vt you can write it as square root of gamma r dt. By the way, the r here is gas constant, which we all know it's a universal gas constant divided by molecular weight of the gases. So this is also given. So basically everything is given. Now let's try to plug in the values and try to get the answer. So pressure at the throat we just found out, 19.49 atmospheres, 101,325 divided by R. You can write it as 8314.5 divided by 23.30 into the throat temperature we just found, 3276.79. 3276.79. Alright, now we have square root of gamma RT. Square root of gamma is 1.4, 8314.5 divided by 23.30. Please mind the the units here and here. So what I did is I changed it to joules per kg, joules per kilomole, and then I directly substituted it to get joules per kg. Okay, and now you multiply this with 3276.79. So does anyone have answer for this?
Very complex.
So maybe you can find first what is velocity of the throat. E 314.5 divided by 23.3 into 3276.79 into 1.24. So for me it is coming out to be like velocity of the throat is 1204 meters per second. Okay, and let's find the density of the gases at the throat. So it's coming out to be 1.49 and 155, 8314.5. So density of gas is coming out to be something like 1.688. So this might be wrong. Please cross check this once. So if I divide it, if I calculate it, for me it's coming out to be, area of throat is coming out to be 0.1967 meter square. This is what I'm getting. I might have done some algebraic mistakes, but yeah, please cross check once. Okay, this is one way to find out. Can you guys guess another way to find out this? Here we are finding density of the gases at throat and velocity of the gases at the throat. All these things we are finding, and then we are trying to come up with the area of the throat. So there should be another way to also to find out this. Any idea? we know a formula about m dot relation with PC and you know PC in the sense chamber pressure and chamber temperature with m dot. So there is actually a formula for that. Do you guys remember that formula? So there is this characteristic velocity we studied, right? C star equal to PC AT by m dot. So here m dot is given, PC is also given. Only thing is we need to find C star. If we find C star, we can directly find the area of the throat. So area of the throat we can write as m dot C star by PC. But how do we find C star? So C star we
It
have,
too has a formula.
right. So we have something like
Under
one.
root.
I think
Uh,
it should be something
so
like
under root RTC upon capital gamma.
Tc by molecular weight. Let's say if I
Ah,
write
yeah, we
it,
can use. Yeah,
and
yeah.
it is
Capital
something like
gamma is also
capital
again.
gamma, right? Something
Right.
like this. So here also we know everything. You can find it, you can substitute here, and based on PC and m dot which is already given, you can directly find the area of throat. This is also same. Basically what we did was uh, we converted the uh, you know we converted the chamber temperature to a throat temperature and also to throat pressure, since we found out before. We use that to get this relation. So basically this relation and this relation are nothing but same. Okay, these two are same only. So let's say instead of you finding this, you change this in terms of, since it's a pressure at the throat, right? The pressure at the throat we just expressed it in terms of pressure at the chamber, and if you substitute all of these things together in this relation, you will ultimately end up with this relation. So basically both are same. Both, that what does it say is mass flow rate. Mass flow rate is constant, and you can directly get the area of throat based on that. Okay, so these are just formulas.
One thing I guess. So the 80, the values that you have put for the above equation, I think 23.3 to 10 to the power minus 3 must come there.
So you mean to say here this one
Yeah, yeah. The
into 10
denominator part here, minus 3 and that one also. That under root one also. Because
but
this thing, yeah.
No, they've actually given kg per Kelvin, kg per kilomole.
Yes. Okay. kg per kilo.
it's given kg per
Okay.
kilomole.
kg per kilomole. Okay.
So what I did was I wrote the gas constant in terms of kilomole. It's not 8.3145, it's 8314.5.
Okay, okay.
So
That's right.
yeah, you can write 8.3145 into divided by 10 power minus 3, you can write, which is going to give you kg per mole, and the mole gets cancelled, you will end up with in kg. Okay, so either way you can write. So whatever you said is right. There will be 10 power minus 3 that I took up and multiplied with 8.3145. Okay, any other doubts? So basically we are done with the first question, and next is we need to find the exit Mach number. Now let's try to find out the exit Mach number. So the principle is same. We need to, it's going to be same mass flow rate only. So let's see, how do we find the exit Mach number? Any ideas you guys have? There are multiple ways in finding it out. So what I'm
You can
trying to
find the
say is,
velocity in the mass flow
please,
rate.
please, yes.
You can find the velocity using the mass flow rate.
Okay, we can find velocity using the mass flow rate. Velocity at the exit. How do we find out velocity at the exit?
Uh,
Using mass flow rate. So what we know is mass flow rate is rho exit, A exit, V exit. We don't know any of this. Only we know is mass flow rate.
yeah.
So A exit, area at exit we can determine, I guess, no, with the area ratio.
Area ratio is given. I don't think so.
And we can calculate. We have PC and PE both.
Okay, area ratio we can calculate. So that's actually the third question. Uh, we need to find the
Expansion
expansion
ratio.
ratio. But
Yeah, yeah.
anyway, area ratio if you want to find, you need to have you don't need to have Mach number in it.
No, so
Oh,
Mach number
okay.
is not required. Only PC, PE, and gamma.
So how do we find PE?
E is given. It is designed for
Okay,
atmospheric, sea level atmosphere.
okay. So that's what I was expecting. So basically, this is unless you don't know the exact conditions, you won't be able to find this. So
Yes, sir.
first we need to find P at exit. P as exit is given as we are going to. It's an ideally designed for sea level condition. So P and exit is 101,325 uh, pascals. So 1 atmosphere basically. So from here what you can do is you can actually find the, you can directly find the exit Mach number using the same isentropic relations, using the same relation. Only thing is, instead of throat you have uh, you know exit, but this relation is not valid because we already consider Mach number to be equal to 1, but here you will have Mach number here. So let me write down that. So P what would be that relation? It's going to be, so what we already wrote was T stagnation by T is equal to 1 plus gamma minus 1 by 2 m square. So if you want to do the same for PE, so P stagnation by P is going to be what we also wrote. So I am actually very weak in remembering formulas, so that's why I'm, so P stagnation, so this is 1, P stagnation by P is equal to T stagnation by T whole power gamma minus 1 by gamma. Okay, T stagnation by T whole power gamma minus 1 by gamma. So now you can just directly substitute here. P stagnation, actually people usually write stagnation as naught, so let's just follow that, equal to 1 plus gamma minus 1 by 2 m, sorry, m square should be inside, so whole power gamma minus 1 by gamma. Now we need what we know is this stagnation pressure is the chamber pressure, and what we need to find out is P at the exit. I mean, we know the P at the exit, we need to find M at exit. So we can write this relation as into P into 1 plus gamma minus 1 by 2 m E square whole power gamma minus 1 by gamma. Okay, so this is PC and this is PE. So this you can write it as PC is 35 atmospheres, this is 1 atmosphere, and let's say you take all these things on the other side, gamma minus 1 by 2 m exit square is equal to 35 power gamma by gamma minus 1 35 power 1.24 by 0.24 minus 1 into 2 by 1.24 minus 1, and then you take the square root of this. You will end up getting Mach number at the exit. You can directly get the Mach number, or you can just there are multiple ways you can calculate the Mach number. You can write it as velocity at the exit divided by square root of gamma or t at exit, and you can find t at exit using this relation. You can find t at exit, and v at exit is nothing but the jet velocity. We know from the previous weeks it is going to depend on pc, tc and molecular weight. From there you can find the v at exit, you can find t at exit. Once you find v at exit and t exit, it's a Mach number at the exit you can find. But principally all these things comes from the same relation. Okay, it's just for our convenience we wrote it in a different ways. So how much is this coming? Looks like I made a mistake during writing the relations. So what did I write? I think there is some t by tc. So P by PC, I think it should be gamma by gamma minus 1. So it's T by T naught is equal to P by P naught whole power gamma minus 1 by gamma. So we are writing in the other side P by P naught is equal to T by T naught whole power gamma by gamma minus 1. So P by P naught is equal to T by T naught is you can also write T naught by T whole power gamma minus 1 by gamma. This can be written as 1 plus gamma minus 1 by 2m square whole power gamma minus 1 by gamma. Is this the same? No, I wrote it reciprocal. Okay, so it's P by P naught. Because this is also P by P naught, T naught by T. Okay, sorry about that. So if that is the case, then this is going to be reciprocal. So P exit PC.
So the pressures and temperature are directly proportional. So
Why is that?
from the equation that we have derived this relation, P by P naught, T naught by T to gamma minus 1.
So actually you should check the
Sir, it is actually gamma upon gamma minus 1, that temperature power, I think, as far as I know.
this
The
one,
power
right?
over,
This one,
yes sir, it is gamma upon gamma minus 1.
gamma by gamma
And
minus 1.
yes, so it's P naught by P only, I guess.
Yeah, both are actually same, right?
Yes, they both are actually same. Pressure and temperatures are proportional
Uh-huh.
directly.
Okay. So, but I reciprocal this, so I reciprocal the power also. Doesn't it work like that? Okay, anyway. So gamma by gamma minus 1.
So you don't reciprocal the power, the power remains the same.
Yes,
Okay.
I guess.
Yeah, 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 yeah. All right. So then what happens here? It's going to be PCP. This would still be 35, but this is going to be gamma minus 1 by gamma, right? So this will be 35.24 by 1.24. And now I think it should come right. So how much is the Mach number you guys are getting? So I'm getting something like 2.872. Alright. So whenever you are in confusion, if you forget the formula, is just this old thermodynamics uh, thing. So P1 V1 power gamma equal to P2 V2 power gamma. From there you get what is the relation. So if you remember this relation, and if you know this relation, you can find everything else. You don't need to remember any formulas. Okay. So I thought I will just write the formula and save your time, but it looks like I made a mistake. Alright, so Mach number is 2.87 is what I'm getting. I hope that is what you guys are also getting. Okay, thanks Tanisha. Alright, and what we also need to find, we need to find expansion ratio. And for that we'll use the formula, because the formula is already derived in the class. So let me write down that big formula. So during that time you guys can find the solution and give it to me. So it is something like
So that expansion ratio, I'm probably getting 3.2.
alright, 3.2. Wonderful. So for the sake of completion, I will just write the formula here. 1 by gamma minus 1 into Pc by Pe power 1 by gamma whole divided by gamma plus 1 by gamma minus 1 to 1 minus Pe by Pc whole power gamma minus 1 by gamma. There will be a square root. So expansion ratio you are getting 3.2.
So the above term is slightly different for what I use. It's 2 by gamma plus 1 to the power of gamma plus 1 upon 2 gamma minus 1. Twice over.
But this is how it should be, right? So 2 by gamma plus 1 into 1 by gamma minus 1 Pc by
So
Pe.
might differ.
So the one we have written, it is not simplified. This is the simplified version.
This is simplified version. You can write the simplified version directly, right? What is
Yes, sir.
this seems correct only, Akhilesh. Maybe can you check once? You meant to say you are you have three terms in your numerator.
No, sir, 2 only gamma plus 1 divided by twice of gamma minus 1.
So
We have the
this
same exact formula. Like it was derived in the video.
Yeah.
which video?
So when numerator has gamma plus 1 by 2 into gamma minus 1, in denominator we have 2 by gamma minus 1 instead of gamma plus 1 by gamma minus 1. So I think
Yeah, yeah.
this formula is correct.
Okay, whatever I wrote is correct, or whatever Akhilesh telling is right.
In the 11th lecture, this
Mhm.
formula is actually derived, like the one you've written on the screen.
So this is right?
Yeah, this is right.
Okay, thank you. So, all right. I don't want to derive this today because it will take a lot of time. So, maybe Akhilesh, you check your notes once. Probably it might be a mistake
Yes,
when you are
sir.
deriving. Okay. So
You
that.
check both weeks first lecture.
Hmm. Okay. So let's say if we do this, what happens? It will become something like this, and PC will be 35 atmospheres, and here we cannot put. We can put in atmospheres also. So, but PE also should be in atmospheres. Did we find PE? We didn't find. Oh, it's just one atmosphere, right? And whole power 1 by 1.24 divided by 2.24 divided by 0.24 into 1 minus 30, so 1 by 35.24 by 1.24. So how much is this coming out to be? So let's say if I calculate this. So I'm getting something like 5.94. Is this what you guys are also getting?
Sir, the on-screen calculator we get during our exams, uh, can we use it now? Like, where do we get it?
Which one? Can you repeat?
The on-screen calculator we'll get when we are writing the exam.
Mm-hmm.
It's a different kind of calculator. It's on
Right,
the screen.
right. Yeah.
So where will we get that so we can practice using that?
So probably it's going to be similar to gate calculator. I guess you can practice with that calculator for your this thing. Uh, yeah, it's going to be similar to that. So I hope others also got the same expansion ratio, and the thrust coefficient, that is again involves a big formula. You can use it to find it, and also actual thrust coefficient if the rocket is operating at 16 kilometer from the sea level, which means at for ideal thrust coefficient we consider that it's a fully expanded, perfectly expanded nozzle, and hence you will not have this P by PC terms, PE by PC minus PA by PC term. But here we have the ambient pressure. They have given ambient pressure at 16 kilometers. So for that, they were asking thrust coefficient, and we were also asked to find the specific impulse. That also you know how to do it. Okay, ISP is simply C star times CF. C star again you can calculate, or since mass flow rate is given, you can always calculate the uh, the thrust, and you can find the thrust at sea level, and based on that you can find the specific impulse. Same thing actually. So maybe I will leave it up to you to calculate all this. uh, yeah, the seventh one is the easy part, so I will solve it. So it's a if semi divergence angle is 15 degrees, calculate the divergence loss coefficient. So for that also we have formula, so we also know how it came, right? So let's divergence loss coefficient for angle of 15 degrees. This is semi divergence angle is 15 degrees. So if that is the case, the divergence loss coefficient, we know that formula to be something like 1 plus cos alpha by 2. So if you you can just substitute it here to find it out. This is in degrees. So let's say if I quickly find out how much is it going. So I'm getting something like 0.9829. Okay. So this is the loss coefficient, but and also what we were asked to find is we were also asked to find the fractional lost in thrust. So this coefficient is basically this is the amount of thrust is lost basically. So this is the amount of thrust is gained, which means the remaining is actually lost. So that's what we were asked to find, the fractional loss in thrust. So that you can write it as something like delta, which is nothing but 1 minus lambda. So which is going to be something like 0.01, how much is this? 71, something like that. Okay. So which means like 1.7% of the thrust is lost because of this, because of the flow not being, axial. Okay, so because some radial component is there, because of this 1.7% of the thrust is lost. That is the real meaning of this fractional loss of thrust. And determine the exit area of the nozzle and calculate the divergent length of the nozzle. Okay, exit area you can find out because we already have expansion ratio. You can find out the exit area. That is going to be simply expansion ratio is nothing but area of exit by area of throat. So area of exit is some 5.94 times area of the throat, which is 1.1967. So 0.1967 times 5.94 is 1.1684 meter square. And then we need
to.
Yeah, sure.
Isn't it area ratio? Why do we also call it expansion ratio?
Basically, what happens in the nozzle is expansion. And it also directly depends upon the area. If you have a higher area, you are going to have a higher expansion. So that is the reason we also call it as an expansion ratio.
Okay.
So divergent length, they are also asking divergence length, which means we have a nozzle and this is our divergence portion of the nozzle. They were asking this is the throat, and this is
the radius of both,
right. We need to know the radius of both.
The difference.
We actually just need the ratio, so we can take the ratios of area. We can do pi d square by 4 divided by pi d square by 4. Play around there.
Right. So we have to do that. Since we know the area, you can find the diameter, and then you can find the radius. And LD is going to be simply, you can use the trigonometry. So let's say this is the alpha 15 degrees, right? So this is like kind of right angle triangle, and this is going to be RE minus RI, and this is the length LD. Okay,
part of that angle multiplied by the difference.
Right, yeah. So RE minus RI into part of alpha. So basically tan alpha, you will write it like RE minus RI divided by LD. So then you can replace it with cot alpha. So I guess this is also pretty straightforward. I guess you guys will do it. I will leave it up to you. So basically, yeah, all these are done. And the thrust coefficient we already did last time, so I'm not going into that again. So if you have any doubts, you can ask. I hope this question was pretty straightforward for you guys. Let's do something more interesting. So we will continue this in next class also. So what this question is about is, this question is about some combustion. So this is the physics which is going to happen inside the combustion chamber, and these are the things which is going to determine your chamber pressure and temperature. Okay, chamber pressure, temperature, and also the gas mixture at the in the chamber. So it is this question is based on that. Before I go into second question, do anyone have still have doubts with the first question? Okay, I will take that as a no. So in the second question, what we have is we have a fuel-rich mixture of dodecane. Dodecane is kind of like a fuel. Okay, C12H26. It's a hydrocarbon fuel, and oxygen also. So if we have fuel, we need to have oxidizer in order for it to react. Okay, so and the oxidizer we have here is oxygen. Okay, and that standard condition is burnt in a rocket chamber at a mixture ratio of 2.6. So mixture ratio, you know what is mixture ratio, right? So it's what do you call the mass of fuel by mass of oxidizer is what mixture ratio. And assume that the more reactive hydrogen in the fuel is initially oxidized to H2O, and subsequently carbon present in the fuel is first oxidized to CO and thereafter CO2. So basically they are telling you how the oxidation is happening, but ideally this is not what happens in the chamber, but you can approximate the whole process with these statements. So what they are telling is, since we have a hydrocarbon, the hydrogen is also going to get oxidized, the carbon also is going to get oxidized, and they are telling hydrogen is more reactive, so that can easily oxidize. So consider that hydrogen is fully oxidized to H2O, and then remaining you oxidize first the carbon to CO and then oxidize the CO to CO2. That is what they are telling. So basically they are kind of giving you a simplified reaction mechanism. This is nothing but a simplified reaction mechanism. Okay, the heat of formation of CO is given, H2O is given, CO is given, and C12H26. This is nothing but enthalpy of formation. Now what we are asked to find out the moles of all product species. Yes.
So which one is for carbon dioxide? Yes, both are.
Oh, okay. I'm sorry. I think the first one is carbon dioxide. Let me quickly check that.
Yes, I guess first one is.
Right. Yeah, it's the first one is carbon dioxide. So sorry, this is carbon dioxide. Okay. So what we need to find is we need to find the moles of all product species. We need to find the molecular mass of the product mixture, find the heat of combustion, and then we also need to find out adiabatic flame temperature and C star. Okay. Alright, so let's try to find this out. This is a fuel mixture of C12H26 and the oxygen at standard condition. So basically what is the reactant we have? We have C12H26 and then we have oxygen. Okay, and this is going to react and give you products. So what are the products we will have? So mixture ratio is given.
So it must be water and CO.
Okay, water and CO. H2O I will have, CO I will have, and then
CO will react with more of oxygen to the CO2.
That is also given, CO2. But in reality, what and all it can form?
Only water and carbon dioxide.
Okay, interesting question. I mean, interesting answer. Water and carbon dioxide. So in reality, you are telling that only water and carbon dioxide will be formed.
Yeah, there used to be some formula kind of thing when we studied chemistry. It was a long time ago. I don't remember it.
Okay, so but that is not actually true. In reality, I will write. In reality, the whatever the it's called incomplete combustion. Usually, doesn't complete combustion doesn't happen. Only if it is a complete combustion, you will end up getting your desired product species, which is CO2 and H2O. After CO2 and H2O, no reactions can happen.
Yeah, yeah.
Okay, but in reality, there will not be any complete combustion. That is for sure. Okay. Additionally, what will be there is H2, O2. You can have anything actually. You can have CO is already written. You can have O3. You can have what else? Since you have C12H26, you can have all hydrocarbons. All these hydrocarbons are actually called as soot. In fact, in let's say in any automobile engines, if you take, you will see this black dusty gas coming out. So those black things are actually hydrocarbons. So those number of hydrocarbons will be there. And in addition, yeah, basically all these things will be there. Okay. And so can we find what are the moles of each and every of things of this? Is it possible to find it out? What is the number of moles? How do we find number of moles? Is it possible to find everything? So if you look at the question, you have actually what has been given is C12H26, which means like you have some number of carbons, some number of hydrogen atoms are there, some number of oxygen atoms are there. Now you have only 3 atoms and whose configuration is given. So how many atoms are given? But I am telling I will have lot of products and I want to find each and every product. What is the number of moles of each and every product? That is basically not possible, depending on just knowing the number of atoms present in the reaction system. So let's try to find out. So you will understand it more once I do this. So let's first try to find out what would be the number of moles of oxygen we require. Okay. So we will use the mixture ratio. So mixture ratio, we all know it's nothing but it's a mass of it's a fuel rich mixture. Yeah, mass of oxidizer by mass of fuel. Okay. Now let's say you consider 1 mole of fuel has been used. So if you consider 1 mole of fuel, mass of oxidizer, you can write it as number of moles of oxidizer times molecular weight of the oxidizer divided by mass of the fuel. You can write number of moles of C12H26 divided by molecular weight of C12H26. This is, I am telling, it's equal to 2.6. Okay. And what I am interested in, number of moles of O2. So molecular weight of O2 is known, that is nothing but 8 plus 8, 16, right? And molecular weight of C12H26, H26, right? Yeah. So how do we find C12H26? It's 12 times 12 plus 26 times 2. So it's something like 196. Okay. So 196, let me write the units also. So 196 grams per mole. So this is the molecular weight of the O2 and C12H26. So and number of
So for O2, I guess it is 32 molar mass.
Oh, okay. Sorry. So C12 H26 is 196, right? C12H26. So
So it is
carbon is 12.
170.
170, I guess, yes, sir. 170 plus 2.
26, 12 into 12.
and 26 into 1, yeah, 170 it must.
26 is 170, sorry, 170 grams per mole. Okay, and number of moles of C12H 26 is also given, so you can write this as into 1 into 170 divided by 32. So how much is this coming out to be? So I'm getting something like 13.81. Okay, so
Yes, sir.
so 13.81. Okay, so I'm telling I have 1 mole of C12H26 and 13.81 moles of oxygen, and I'm expecting you to find all these things. Is it possible to find? I mean, for a moment you can forget these lines. We'll come to that. But is it possible to find all these product modes? Let's say if you want to find, how will you find? You basically do atom balances, right? You will just balance the reaction that we did in chemistry classes. So can we just balance the reaction and find all these? Is my question. We don't even know how many species are there. So let's say, for example, I will remove this. This is what is this. Let's say I assume that there is no hydrocarbon present and everything is formed like this. Is it possible to find all this?
Not by attention.
Not. Okay. So
There are too many unknowns. Can't do it.
Yeah.
so basically there are actually, you have only 3 atom balances. What are those atom balances? You have carbon, hydrogen and oxygen, and I'm expecting you to find lot of n product species.
Sir, this is oxidation reaction. So in the product side, why a single O is forming?
Why not? It can't form. O has to, if I want to form CO, then O2 has to break into 2 O's, right? And 1 O can react with the carbon and become CO, but other O can just remain like that. There is no reason for it to form O2. There is no reason for it to be O2. So that statement is not entirely true. It depends. It depends on the temperature. Depends upon various things. So that I will come to it soon. But O can remain just as O. There is no reason for it to become O2 also. So we can have any of this. This is actually true in real situations. Let's say if you take the rocket and if you just fire the rocket and you collect all the exhaust products, and then you check concentrations of each and every species, you will always have all these things. You will have ozone, you will have H, you will have H2, you will have O2, everything you will have. You will have CO, CO2, H2O, everything you will have. If you do, in experiments, if you do it. And we couldn't find what are these things, which means we are missing something, right? So I have like something like 1 2 3 4 5 6 7 8. I have like 8 unknowns, 8 product moles I need to find, but I have only 3 atoms, 3 atom balances. So basically I have 3 balance equations, atom balance equations, and I am trying to find 8 unknowns. So it is not possible. So what is missing then? So atom balance is nothing but, as I said, I would like to repeat once more. In reality, you need to just consider the only three. There are only few principles, for any system. One is mass conservation, momentum conservation, and energy conservation. So in this case, you can forget the momentum conservation. We are not interested in forces and all. We are just interested in what is the energy conversion from here to there. Okay. Now, and also we use atom balance is nothing but a kind of a mass conservation. It's nothing but a mass conservation. So with the three mass conservation, three atom mass conservation, we were able to get only three. Uh, you can get only three unknowns. But how do I get the remaining five unknowns? Let's say if you consider the energy balance also, we also need to find the temperature. So since the reaction is happening, this will be at a different temperature, right? So that temperature will be found by energy conservation. So still we are left with five unknowns. We don't know the other product mole species. I mean product moles. Okay. So what is the important principle we are missing? Can anyone tell what is the important principle? So I have mass conservation, energy conservation, momentum conservation is irrelevant here. Some important principle we are missing. Because of that, we were not able to find the remaining unknowns. Can anyone guess what is that principle? It has to do
Sir,
with
stoichiometric.
stoichiometric is what we are what do you mean by stoichiometry? It's basically balancing equations, right? What stoichiometry has to do here?
Sir, same as the coefficient, the number of moles.
Stoichiometry for stoichiometry you will consider ideal products, and what do you do is you will make a mixture ratio will be like, not mixture ratio, the equivalence ratio will be 1, right? Based on that, you will find, if you will just consider the ideal products, which is going to be H2 and CO2, and those moles only you will find. But I am telling, in real system that is not happening. I am telling you will have all these things. You will have all these 8 species, let's say. So how will you find? What is the principle behind we are missing? You guys want to take a guess, or should I tell the answer? So this is nothing but mass conservation. And energy conservation we need to use for temperature. We need to know the temperature of the mixture, right? So once the reaction happens, temperature would be high. That we are going to find it using energy conservation. So you have 3 mass conservation, 1 energy conservation, total 4 equation, and you have 8 unknowns plus temperature, total 9 unknowns. So what to do with that 5, remaining 5? And what is the principle which is going to govern this? Alright, you guys are thinking too much. Do you want to take a guess, or? So there is some principles we missed in thermodynamics. There are few laws of thermodynamics, right? So we have something called first law, and we have something called second law. So first law is nothing but simply energy conservation. Okay, this is energy conservation. So these two are basically the same, but we didn't consider this second law at all till now, right? So second law tells that entropy of universe should be maximized. So which means the second law is going to govern what is going to be my individual species, product moles, or individual mole fractions of each and every product mixture. So second law tells what is a favorable condition you can have, because and that is going to dictate what is going to be your mass fractions or moles of each and every product species. Okay, so this is one of the thing we were not using till now. We were not using second law till now, and eventually we ended up having very high number of unknowns, and which which led to closure problem for us, and which lead to consider the second law in it. Okay, so this is something I wanted to stress, is because any the process which happens, it's going to follow certain guidelines. So that is, I mean, we only found these guidelines, found these laws, uh, but if you find that there are more unknowns, which means you are missing certain principle, and here it turns out to be second law. And using second law, you will be able to get that remaining 5 equations. Okay, this is what we call it as an I think it's chemical equilibrium calculations, which I will not go in detail, but you can learn for yourself. So using this second law, you can find the remaining, you can get another 5 equations. Okay, and you can close this whole system, and you can solve it together to get the number of moles. Okay, so this is some extra information for you. So I think you guys must have done a preliminary. I think professor must have taught you preliminary, second law, chemical equilibrium analysis things. You can go and recheck that. So basically, it's just a principle. We need to implement second law in order to get the other things. But for now, what we are going to use is, since it's been given that's why these statements are given. If not, there is no reason for this statement to be given. So if these statements are not given, I am going to have all these species, and I won't know how to do this problem. That is why the statements here is given. Okay, and they are telling hydrogen is more reactive, and so it forms H2O, and all these statements are actually the result of second law. So second law is telling that if I make the hydrogen to be reactive, then my entropy is going to be rise, and that is a favorable condition, right? So that is how these statements come into picture. So for our problem, what we will do is we'll just consider this. Ouch. Okay. We'll just consider those 3: C12H26 plus 13.8102 gives, we'll just consider just H2O, CO, and CO. Okay, so all the other species actually we eliminated after considering second law. That is something you can keep in mind, and that elimination is coming from because of these statements we have here. Okay, so you can implement these 5 equations, and you can solve it. All these things can be possible, but it cannot be possible by hand. You need to have a computer, you need to have certain numerical algorithms in order to solve it. We can even discuss about this a little more maybe in the next class if time permits. Okay, but for this question, since these are given, we can take only these 3 as a product species, and you can go forward and solve. Okay, is there any questions you wanted to ask about this? So no one is going to ask you to do this chemical equilibrium calculation. This is just for your additional information, because you might ask me why the hydrogen has to react and form H2O, why CO has to form first, why not directly it forms CO2, right? And this is the answer for those. So if there are no questions on this, let's go forward and solve this. How we may need to let's say we'll consider this as A, B, and C. since you have A, B, and C only three unknowns, and you have three atom balance, now the system is closed, so you can directly solve it. So you have, let's say for carbon you have 12 on the LHS, and here you have B plus C, and for hydrogen you have 26, here you have 2A, and for oxygen you have 2 into 13.81, here it is A plus B plus 2C. So from here you can get A to be 13, and what else you can get? So you have B plus C equal to 12, and B plus 2C is equal to 2 into 13.81 minus 13, which is going to be 14.62. So from here you can do minus C equal to minus 2.62, so C equal to 2.62, and B is equal to 12 minus 2.62, 9.38. So this made our life easier, actually, those things. But one thing we actually missed, so this is not actually right. So B is 9.38, and this is 2.62. So here what we didn't consider is, we didn't consider that hydrogen has to be oxidized fully first. Those things we didn't consider. But still you can write this as, so let's say if you want to consider that, so you have 26 hydrogen atoms, and you are oxidizing everything to H2O, which means you are going to form 13 H2O, which means I lost 13 O's to the hydrogen. And then what you have is 12 carbon atoms, and with that I am first forming 12 carbon monoxides. So I have 12 CO. So if that is the case, how much O I will be left with? So I will have 13 plus 12, which is around 25 O's taken. Total I have around 2 into 13.81 is 27.62 minus 25, which is 2.62. So this actually gives us 2.62 O left, okay, after these two oxidation. So since 2.62 O left, what I can use it to oxidize few of the COs. So if 2.62 O is left, then I can use 2.62 CO plus 2.62 O to oxidize and give 2.62 CO2. Okay, and if I get 2.62 CO2, then how many CO I will be left with? So I will have 12 minus, it will be, so this will give us 9.38 CO remaining left. Okay, this actually provided that mixture contains 13 H2O and 2.62 CO2 and 9.38 CO. So luckily what we do here actually turned out to be same. Okay, the reason is you have three unknowns and you have only three species. Sometimes in your equation you might have more than three species, and you may need to properly follow this procedure in order to find the proper concentration of each and every species. So since here it is like three unknowns and three equations are there, its system is determined and you can just go forward and solve. Let's say if I have additionally O2, okay, then depending on the statements given in the question, you need to follow this kind of steps, how much you can convert, how much you cannot convert. Based on that you can arrive at this mixture concentrations. Okay, is that clear? Did I go too fast? So basically we are just following whatever they gave. Okay, and based on that we found the moles. And so this is done basically. So what we need to also find is molecular mass of the product mixture. And what is the molecular mass of the product mixture? So it's nothing but mole fraction weighted, or you can also say, yeah, or you can write this as where I equal to some any species, Ni molecular weight of I divided by summation of Ni, summation of Ni molecular weight of I divided by summation of Ni. Or this also can be written as summation of xi mi, where xi is mole fraction. Okay, so since we know the number of moles and we also know the molecular weight of each and every species, you can write this as NH2O molecular weight of H2O plus NCO2 molecular weight of CO2 plus NCO molecular weight of CO divided by N of H2 and CO2 N of CO. Okay, now let's substitute these things. We will have 18 and
2.62 into 44 is
is it 12 plus 32? Yeah, 44.
44, and 9.38 into
12 plus 16,
16, like 20,
8.
28, 28.
Okay, divided by 18 plus, sorry, not 18, 13 plus 2.62.
2.62 plus 9.38. It's about coming out to be 24.48
Wonderful. So it's like gram per
gram per
mole
mole.
or
Gram per mole.
kg per kilomole. Both are actually same. So this is how we find molecular weight of mixture. This is straightforward, you guys know. Only critical part is how much number of moles you need to find. Once you find this, these things will be easier. Now we need to find heat of combustion. So how do we find heat of combustion?
So the negative means the heat is released, I suppose.
Okay.
I'm asking you.
Yeah. Negative means it depends upon the system. If the system gives the heat, then it becomes negative, and if it is gains the heat, it is positive. It's just a convention that we take.
Yes,
But what is the heat of
sir.
combustion? So we find something like delta Hc. So what you guys like very much is you guys have the formula and you just want to implement it. Let's say if I give the formula, so it might be something like I think it's like H of products at 298 Kelvin minus H of reactants at 298 Kelvin, I guess. By the way, there will be minus because it's a heat of combustion. Or I don't know what professor wrote, maybe something like summation of Ni HFI. HF is like a heat of formation or enthalpy of formation of reactants minus summation of Ni HFI of products. Right? This is the heat of combustion. I hope this is what professor told. But what is this heat of combustion? Is physically, what does it mean? I'm not really fond of these formulas. If you understand it physically, you can easily understand what you should do to find this out. So, does anyone want to try what is heat of combustion is? Do you have any definition or understanding of what is heat of combustion?
Is it the heat that is used for the reaction? Like that is necessary for the reaction? Like,
Mm,
Is the heat released when the reactants are combusted,
okay.
depending on the aroma?
Yeah, actually, it's partially true. It's not entirely true. So, what this heat of combustion is the amount of heat released. Okay, amount of heat released during combustion when the both reactants and products are at same temperature. Okay, the temperature is not changing, please understand that. So let's say if I want to make you understand this, let's say you have some box. In our case, it's nothing but a chamber. For example, you consider this as a box. Okay, in the box we have some C12H26 and some 13.81 O2 oxygen. Okay, and this is an adiabatic box. Okay, now let's say it combust everything. What happens to, so I'm drawing a bigger box. It's the same box. What you have is you have H2O, you have CO2, you have CO. Okay, this is also adiabatic. But during this, what happens? So this is what reaction is happening. So this is at 298 Kelvin. Okay, for example, I'm taking. So reaction has happened. What will be the temperature here? It will be some temperature, right? It will not be 298 Kelvin because reaction has happened. A lot of heat will be released, but heat is not going out because it's an adiabatic wall. So there will be a higher temperature, some T higher. Okay, now what I am trying to do is, what I will do is I will remove this adiabatic. Okay, I will convert that into, I have another box. So what I do is at this point of time, once the combustion is complete, what I do is I slowly, what I will do, I will start getting out some heat. I'm trying to get the heat from the system. I will get this out until the temperature here again reaches 298 Kelvin. Okay, and this Q is nothing but the heat of combustion. Okay, it's not like the amount of heat released, but it also depends on the exit temperature of the products. If you let's say if it is 298, here it is going to be 298 Kelvin. Heat of combustion is defined at 298 Kelvin. Okay, so at 298 Kelvin, if you have a reactants and if you let it combust, and if you remove all the heat from it to make the product also at 298 Kelvin, the amount of heat you remove during this process is what the heat of combustion. And this heat of combustion is purely due to the chemical energy which was stored in the fuel and oxidizer. So there was some chemical energy stored in the fuel and oxidizer, and that is taken out. And what is the amount of heat the amount of heat is equal to the amount of chemical energy stored inside the fuel. And how does the chemical energy get stored? It's because of the chemical bonds, right? So based on that chemical bonds, if you break those chemical bonds, if you oxidize it, some energy is released, and those energies, if you collect it out, that energy is called heat of combustion. So if you increase the temperature, if you allow the temperature to rise, you will be using some energy to increase the temperature, right? So that energy we are not accounting. We are trying to find out what is the maximum amount of energy that I can get from the system. That is why it's called heat of combustion. Let's say if I have products, if I completely combust it, and if I bring the product down to 298 Kelvin, then I will get some amount of heat. That heat is nothing but the heat of combustion. That is how this combustion is defined, which means whatever the energy you get is equal to the chemical energy stored in the fuel. Okay, so that's why we write it as the chemical and the formation energy is nothing but the energy required to form that bonds. So this formation energy of reactants minus the summation of formation energies of the product is giving you the heat of combustion. That's why you have such formula here. Okay, is that clear? So if it's clear, let's try to solve this. So summation of reactants means N of C12H26 into H formation of C12H26 plus N of O2, H formation of O2 minus N of H2O, H formation of H2O plus N of CO, H formation of CO plus N of CO2, H formation of CO2. Okay, since we know the number of moles and H formations is also given, but you might have noticed that H formation of O2 is not given, right? H formation of CO2.
It is often taken 0. It has been stated.
Yeah.
Often taken 0.
It's actually the reason to often take to 0 is we are actually defining it like that. Whichever the element is in its naturally occurring state at standard pressure and temperature, if it is naturally occurring in that state, then we take it to be 0. For example, the H2O here is in vapor state, so we cannot take that to 0. But O2, it will be in vapor state at 298 Kelvin, right? At standard temperature and pressure. So that's why you take HFO to be 0. Okay. Otherwise, everything else would be given. Okay. And
so then, what about CO and CO2? They are also.
Okay. So it's CO and CO2 naturally occurs at it is also should be naturally occurring element, right? So in our case, O2 is a single element. So CO and CO2 are not an element; those are molecules. So those are in order to form a molecule, you need to spend some energy. Okay, that's why. So this HF of O2 we take it to be 0 because we define the datum there. Okay, and from there we are trying to get what will be the enthalpy. Always we are interested in enthalpy differences during this because we wanted what is the amount of energy we need. So yeah, so that's why you have formation and enthalpy for H2O, CO, CO2 but not O2, but O2 because it's a 0. Similarly, formation enthalpy of hydrogen H2 is also 0, but formation enthalpy of hydrogen atom is not 0 because naturally it occurs as H2. So if you want to divide it into H, you need to spend some energy. So that will be the formation enthalpy for H atom. Similarly, for O atom, it is not 0 basically. So for O2, H2, N2, all these are formation enthalpies are 0. Okay. So then I think from here it's straightforward. You have formation enthalpy of C12H26, formation enthalpy of H2O, formation enthalpy of CO, and formation enthalpy of CO2. What are these? I need to copy from here. Minus 390 minus 298. Sorry. Minus 390 minus 278 minus 112 minus 159. I think all are kilojoules per kg. Kilojoules per mole. All are kilojoules per mole. So you multiply the number of moles with it, and then you substitute it in this relation, you will end up getting heat of combustion. So this will be the amount of heat, which maximum amount of heat which you can extract from this reaction. So that is why it's kind of like a parameter which you can use it further for your analysis. So since we lack time, what I will do is I have some answer here which I solved it before. It's coming out to be 35632.75 into 10 power 3 joules, or you can write this as kilojoules. Okay, so it's just direct substitution, so you might end up getting this. So this is the amount of heat which will be released during a reaction given that product and the reactant are at the same temperature. Okay, that is very important. These two should be at the same temperature, and the temperature should be equal to 298 Kelvin, because delta Hc is defined at 298 Kelvin. Okay, so this and this should be at same temperature, and the amount of heat you get outside of it is what the heat of combustion is. Okay, and we were also asked to find adiabatic flame temperature and C star. That what I will do is I will continue this, and in the next class what we can do, we can finish this question of adiabatic flame temperature and C star. Okay, so we will also try to understand what is this adiabatic flame temperature, why the name adiabatic flame temperature, and how does it related to any of the calculations that we are trying to do. Even you will be asking why I need to find heat of combustion. I'm not very much interested in heat of combustion. How does it going to help me in quantifying the performance of a rocket, right? So all these questions we will answer, and so that actually is going to affect your C star, and C star is what is going to affect performance of your rocket. So what we will do is we will continue this discussion, and we will solve this problem in addition to next week's problem, because we ran out of time today. Okay, so does anyone have any questions in the I think I might have rushed a little bit. Maybe we can recap also in the next session. If you have any questions, you can ask me. Does anyone have any questions?
So when is the next class going to be? Monday, Saturday?
So it's going to be every week, every Saturday, 7 to 9.
Okay, yeah.
So next class will be around next Saturday, 7 to 9.
17, yeah.
Alright. So if there are no questions, we can meet next class. Okay. If you have any questions, you can stay back and ask. No problem. I will be here for like another 10 minutes or so.
Thank you, sir. Thank you very much.
Thanks, Sakhilesh.